We're now talking about muscle tension and skeletal muscle, section 6 of muscle tissue, chapter 10 for anatomy and physiology. For this section, you should be able to describe what occurs in a muscle during a single twitch and relate each event to a graph of a twitch. Explain the events that occur in motor unit recruitment as the intensity of stimulation is increased. Distinguish between wave summation, incomplete tetany, and tetany that occur with an increase in frequency of stimulation. So with muscle tension, now tension is the force that's generated when a muscle is stimulated to contract. Lab experiments measure tension and graph it. So looking at this muscle here, let me get a little bigger here. This muscle here, we have this muscle here with electrodes here attached to the muscle itself can actually be able to read this myograph here, be able to read actually the amount of tension developed from this muscle, the given amount of weight here, pulling on this muscle, creating tension within the muscle, then to be able to determine how much voltage, basically, and the frequency actually, or the voltage can be given to it and also be measured, I should say. And this pivot here can actually adjust and measure there as well. With hardware detects change of tension in the muscle. And then we can actually assess the latent period where the stimulus occurs before the contraction actually kicks in this contraction period where the height of this contraction then peaks, and then as it's returning back toward normal is the relaxation period in time per milliseconds. A twitch is a brief contraction to a single stimulus. The minimum voltage that triggers a twitch is the threshold. Every muscle has its threshold point. The periods of the twitch are the latent period is the time after the stimulus before the contraction begins. There's no change in tension. The contraction period is the time when the tension is increasing, and it begins as the power strokes of the myosin heads pull those thin actin filaments. The relaxation period is a time when tension is decreasing toward baseline, and it begins the release of cross bridges and the actin and the myosin and release there. And it generally lasts a little longer than the contraction period, generally speaking. Now that said, for changes in stimulus intensity and motor unit recruitment, muscle is stimulated repeatedly. As it's stimulated repeatedly, voltage increases, more units are recruited to contract. So in other words, the more action potentials that are sent or based upon the amount of stimulus that's given to a muscle based on the feedback and the receptors and giving information to the brain and spinal cord, sending information back, firing motor neuron. The motor neuron will fire all of its basically this recruitment is also called multiple motor unit summation. So the multiplicity, so to speak, of all the different motor units combined is basically what we're talking about here. And it's always going to recruit type 1 muscle fibers first, given any given activity. And then type 2A then becomes involved if the voltage is high enough, the stimulus essentially is high enough, requiring enough of a response, a stimulus response with more tension. Then type 2A then becomes involved, and type 2X becomes involved. That's generally speaking. It's always going to go in that general order. The time to which that occurs depends upon the tension that's incurred, depends upon the capacity of that particular muscle, and depends upon the training, basically in genetics, of the person who is involved in that particular activity or that particular stress. It explains how muscles exhibit varying degrees of force. You recruit fewer motor units to lift a pencil, obviously, much smaller number of motor units, versus lifting a suitcase, especially a heavy suitcase. A lot more motor units, so consequently a lot more muscle fibers. And remember that motor unit fires all of the muscle fibers that are associated with it. That basically is called the all or none law. Above a certain voltage, all the units are recruited, of course, for the entire muscle. So the all or none law is basically that when a motor unit fires, all the muscle fibers that are attached to it fire completely. They're on. It's a light switch. It's on or it's off. There's no dimmer switch when it comes to your muscle fibers. They're on or they're off. That's not to be confused with maximum voltage or maximum units recruited, so maximum contraction occurs. That basically, you've got all the motor units of a given muscle have fired. So consequently, get as much as you possibly can from that muscle. That said, there's a point where you keep getting more voltage or muscle, more stimulation, you can't do more. Just like if you were lifting a weight, trying to move a load, and you got a point where you reach your maximum point, it doesn't matter if you add more weight, you're just going to lose capacity to produce force, and you're going to be fatiguing, and you're not going to be able to produce more force. Recruitment order is always based on the size of the motor units. The smallest are first, and consequently the smallest number of fibers that are involved with those small motor units, those neurons with smaller numbers of fibers. The largest last, also numbers of size of fibers, both in terms of the number of motor units fired, as well as the size of the fibers fired, goes in terms of smallest to largest, the size principle of recruitment. Your body's trying to conserve energy, trying to conserve the potential for production of force, and not give more than is needed. First of all, that wouldn't be helpful, and secondly, it'd be energy draining. And so here we have a skeletal muscle response to change in a stimulus intensity. So as that voltage increment increase here with the millivolts, we're seeing, of course, a greater and greater response here from maximal contractions here. And the relative proportion of excited motor units, you see more and more of them becoming activated, the darker red here, until they're all maximally activated here at maximal voltage, whatever that might be. And the motor unit 1 recruited in smaller fibers here, then motor unit 2 is an example, medium type fibers, so this would be type 1 fibers, be like type 2A and type 2X. It wouldn't be that clean, it'd be more a variety of fibers and numbers, thousands upon thousands of neurons, and the fibers associated with them would be firing for maximal contraction. Now, wave summation, I'm referring to like a change in stimulus frequency. Wave summation is also called temporal summation. If the stimulus frequency is set at about 20 per second, so it's really a high level, relaxation can never be fully completed between twitches, so you can have these overlapping twitches, which helps actually produce more and more force. So essentially anyone that can produce maximal capacities of force beyond most people probably have the greater capacity for this wave summation concept related to the given muscles that are firing. The contractile forces add up to produce higher and higher tensions. Incomplete tetany and tetany, if their frequency is increased further, the myogram exhibits incomplete tetany. The tetany increases and twitches partially fuse. If the frequency is increased further still, like 40-50 per second, the myogram exhibits tetany. The tension traces a smooth line without relaxation, and high frequency stimuli lead to fatigue. Obviously, if you keep increasing that way, there comes a point where the muscle becomes fatigued with decreased tension production, just like in real life, right? So here, we have our frequency of less than 10 stimuli per second. The muscle tension is fairly consistent here as far as the twitches go. And of course, once it gets about 20 to 50 per second, you can see it dramatically increasing that wave summation here until it reaches incomplete tetany where it's almost leveled off, and tetany where it's leveled off at maximal contraction capacity. And of course, at a certain point, not long after that, as we mentioned, for maximal contraction capacity, we're talking about a few seconds. For absolute maximum without any drop off, maximum of 5 seconds. Could be less, 1 second maybe. Okay, before fatigue starts to ensue. It won't drop off the cliff, so to speak, but it's going to drop pretty darn fast. You're going to lose within a few percentage points within a second or two, within a few seconds, and within 10-15 seconds, going to go down about 10-15-20% down, give or take. Maybe not 20%, certainly 10-15% to some extent, depending on the person, their genetics, their training, their capacity, what muscles we're talking about, some possibilities there. So section 10.6, what did you learn? What events are occurring in a muscle that produces the different components of a muscle twitch? The latent period, the contraction, and the relaxation. What's recruitment? Explain its importance in the body. And what happens to skeletal muscle during wave summation? Explain its importance in the body. Now we'll talk about section 10.7 and factors affecting the skeletal muscle tension within the body. We should be able to describe muscle tone and explain its significance here as one of the objectives. Distinguish between isometric and isotonic contractions and give examples of both. Explain the length-tension relationship in skeletal muscle contraction, and define muscle fatigue and explain some of its causes. So muscle tone. Resting tension in a muscle is referred to muscle tone here. We have resting tension in a muscle, generated by involuntary nervous stimulation of muscle. Some motor units are stimulated randomly at any time. Some of it's involuntary, and it's going to be involved regardless of whether you're choosing to do so. Now that said, this muscle tone can change continuously, so units are not fatigued. From the standpoint of certain smooth muscles, cardiac muscle can't stop beating. Certain muscles to keep your posture upright, basically type 1 muscle fiber types, skeletal muscle wise. Some of those muscles can go pretty much forever, or at least year upon year upon year, right? There's certain muscles that have to be active, at least to some extent, constantly. Okay. That said, they don't generate enough tension for movement, these muscle types, okay? And they decrease during deep sleep, of course. You have to be able to rest to some extent, but you can't rest entirely, or you'd be dead. Not a pleasant thought, but the reality of what it would take for a complete stoppage of any muscle fiber contraction. That said, isometric versus isotonic contractions. We're talking about skeletal muscle here. Isometric contraction, although tension's increased, it's insufficient to overcome the resistance. Basically, you're holding in place. If you were actually trying to move something and you couldn't move it, but you're able to hold it in place and it's not moving you and you're not moving it. So if you're holding something in place like an arm curl and you're stuck in place, you can't move it, but it's also not pulling your arm downward, pulling basically your forearm downward essentially. You're able to keep that arm fixed. We have an isometric contraction in that case. Muscle length stays the same. It's holding a weight while the arm doesn't move. Isotonic contraction is a broader term referring to movement here, where muscle tension overcomes resistance, resulting in movement, or not necessarily just resulting in movement, but the capacity to resist that load completely. We'll talk about that in a second. Tone stays constant. Now, tone staying constant, meaning there is some muscle involvement. That's kind of a misleading statement. I'm not really a fan of the way that's often referred because it gives the implication that it's a constant tension. No, not constant tension. There is some tonality, there's some tension development, but length is changing, okay? You're able to control at least a little bit of the motion of the load, okay? There's some control there. Concentric contraction, the muscle shortens as it contracts. In a concentric contraction, you're able to move a load. The muscle is shortening under stress. You're moving something. You're accelerating something. Whenever you push off, you jump. The jump phase of jumping upward. When you take off and run, when you lift something upward or you pull something down, the movement itself away from where it wants to go is the concentric contraction. That said, it's the shortening of the muscle. The eccentric contraction it really shouldn't even be called a contraction. I leave it there, that's the way text refers to it. It's an eccentric action because by definition, contraction is to shorten. We really should call it an eccentric action. Okay, the muscle lengthens as it basically is still resisting load. It's not contracting, it's still resisting load. Okay, you're actually losing essentially. If you're trying to lower it down, is one thing. If it's lowering you down, but you're resisting it to some extent, now there's an eccentric action here. You're still able to control it to some extent. It's not completely making you fall or completely dropping the load altogether, whereby there's no eccentric contraction. If there's no resistance against it whatsoever, you're not slowing anything down. It just moves you, or you have to let go. Well, there's no eccentric anymore at that point. The tonicity is lost. The tension is lost. Muscle lengthens as it is basically active in the biceps brachii when you're lowering a load as an example. Of course, as you know, when people are lifting weights oftentimes in the gym, they don't lower the load, they let it drop, in which case you're not getting any benefit from eccentric activity, which is unfortunate because the greatest amount of hypertrophy, which we'll talk about a little bit later, occurs with the eccentric activity, more so than the concentric activity. Be able to control the motion as it returns back to its original position or its desired position based upon the pull of gravity or pull of a machine or whatever you might be working against. Oops, wrong one. Showing here isometric versus isotonic. Muscle tension is less than resistance, basically able to hold in place here, whereas greater than resistance, you're going to actually concentric, you're able to shorten as you bring that baby up, and of course you're able to lower the baby under control, hopefully. Isotonic contraction is your eccentric there, right? We don't even want to talk about if the eccentric there was incapacity to hold that baby. It was a bad idea to pick the baby up in the first place. There'd be no isotonic contraction. No, it's not isotonic activity. And we talk about isometric contraction, and really we should also not call it, I should be clear too, we shouldn't call it isometric contraction either. Again, it should be isometric action and eccentric action, only concentric contraction, technically. It's not the worst thing in the world, but it's just a little off, and it's one of those things that when you know enough, like a lot of things that you are experts in, it bothers you when something's a little bit off. We all do that. That being said, it also responds to an increase in blood pressure. The greater that level of isometric activity, the greater level of blood pressure increase. Sustained isometric activity, so to speak, here is associated with an increase in blood pressure. When someone holds still, obviously that builds up a lot of blood pressure. And we have to make sure we can actually have the capacity to be able to handle it. One of the most important things is to be able to breathe. When people often practice the Valsalva maneuver where they stop breathing in isometric activity, that's a mistake. We should be breathing through it at all times. We don't want to hold our breath. There's too many negatives with that to do that. This may be a concern for those with baseline high blood pressure, obviously. Shoveling snow is an example. If we're talking about heavy snow, that every time some of you get hit, or if you pick up something heavy, your body goes, that little part right there is a Valsalva maneuver. It's isometric activity. For a brief moment, you're pausing with that against that load. That's a natural response to a dramatic increase in stress. What's not natural is to maintain that. Okay? It's not to be saying the same as holding a dumbbell and able to breathe normally. Okay? There's general peripheral constriction in this case here from the cold, which elevates blood pressure, which can be one way that happens. That that shivering, you kind of hold your breath there. Isometric contractions of shoveling also increases pressure if it's again heavy snow. Length tension relationship we're going to talk about when we come back to here shortly when it comes to skeletal muscle.